どうも皆さん、英語で数学、瀬戸です。今回は数列の極限についてミニレクチャーをしたいと思います。今日使う英単語はこちらです。Given an infinite sequence of numbers, we say that the sequence converges to a number L if, for all epsilon greater than 0, there exists an m such that the difference between an minus L is less than epsilon whenever n, the index of the sequence, is greater than some m. So let's look at a quick example. If we want to show that the limit as n goes to infinity of 1 over n is equal to 0, we first fix an arbitrary epsilon greater than 0. By Archimedes' principle, there is an n such that n times epsilon is greater than 1, which means that epsilon is greater than 1 over n. So, if we let m equal n, where m is in the definition of the limit of a sequence, then for n greater than or equal to m, we have 1 over n is less than 1 over m, but this is less than epsilon, so 1 over n is less than epsilon. Now let's try this example. When we want to compute limits, then rather than trying to show by definition, what we would usually do is simplify the expression. In this case, we can factor out an n square from the top and the bottom. These will cancel. And when n goes to infinity, these will go to 0. So what we have left is 1/4. Now let's prove a useful theorem in computing limits. The theorem is that bounded monotone sequences converge. Bounded means that the terms of the sequence is between some number a and some number b for all n. And monotone means that either an is greater than or equal to an plus 1, or that an is less than or equal to an plus 1 for all n. So the first one is a monotone decreasing sequence, and this one is monotone increasing. Let's first prove the case for monotone increasing sequences. We want to consider the least upper bound, or the supremum, of the sequence an. We know this exists because the sequence is bounded. So let's call our least upper bound L, which is bounded above by the upper bound, B. Then fix some epsilon greater than 0. Then consider L minus epsilon. We know that L minus epsilon cannot be an upper bound of an because L is the least upper bound. If this was an upper bound, then this would be a number that's smaller than L, but still an upper bound, which contradicts the definition that it's the least upper bound. So therefore, there must exist some index m such that L minus epsilon is less than or equal to am. But remember, the sequence is monotonically increasing, so we have that L minus epsilon is less than or equal to am, which is less than or equal to an for n greater than m, but then L is an upper bound for an, so we were able to establish that L minus epsilon is less than or equal to an, which is less than or equal to L for all n greater than m, which is an minus L is less than epsilon for all n greater than m. So this satisfies the definition of a convergent sequence. The case for decreasing is similar, except you will consider the greatest lower bound. Now let's investigate this recursively defined sequence. An plus 1 is equal to square root of 1 plus an. A1 is equal to 1. So if we write out the first couple of terms, we'll get something like this. Now, does this have a limit? Let's find out. We first want to show an is bounded. First, we claim that an, the sequence, is bounded by 2. So we will show this by induction. The base case a1, which is equal to 1, is less than 2. If we assume an is less than 2, then an plus 1 is the square root of 1 plus an, but by the inductive hypothesis, an is less than 2, so we replace an with 2, but this is root 3, which is less than 2. And so an plus 1 is also less than 2. What this shows is that since a1 is less than 2, we showed that a2 is less than 2. But then if a2 is less than 2, then a3 is less than 2, etc. And so we show that the entire sequence has to be bounded by 2. Next, we claim that an is monotonically increasing. Again, we do this by induction. We can see that a1 is less than a2. We assume that an is less than an plus 1. Then we add 1 to both sides. We take the square root of both sides. We can do that because it's pretty evident that these are non-negative. But this is simply an plus 1 and an plus 2. So if we have this inequality, then the next step is also true. And so by induction, we showed that this is a monotonically increasing sequence. And so we know that the limit must exist, which is L. So now let's compute it. We take the limit of both sides, but we know that this is L, and this will be L. So now we want to solve for this equation. We have L squared equals 1 plus L, so that L squared minus L minus 1 is equal to 0. So by the quadratic formula, we have that L must be 1 plus or minus square root of root 5 divided by 2. But we know that L is non-negative. So in fact, L must be 1 plus root 5 over 2, which is actually the golden ratio phi. Thank you very much for watching, and please subscribe to our channel.